Nuclear fusion can only happen in the core of a star. It is only here that the conditions of fusion are met. Fusion can occur if the temperature, that is the kinetic energy of the protons, is high enough to overcome their mutual electrostatic or Coulomb repulsion. This is called the Coulomb barrier. For fusion to occur, the temperature must exceed approximately 8 million degrees Kelvin, and the core have sufficient density of hydrogen nuclei for collisions to occur at frequent enough intervals for fusion to be maintained. Fusion of hydrogen into helium, alone of all the possible fusion reactions, produces the most energy output. Fusion produces the necessary outward energy to balance the inward gravitational collapse of the star. When these two forces are in balance, the star is stable, changing very little in its size, temperature and brightness. There are two dominant hydrogen into helium fusion reactions taking place in the cores of main sequence stars. These are the proton-proton chain reaction and the carbon-nitrogen-oxygen cycle, also known as the CNO cycle. The proton-proton chain reaction is one of the fusion reactions by which stars convert hydrogen into helium, the primary alternative being the CNO cycle. The proton-proton chain accounts for about 85% of all fusion reactions in stars the size of our Sun or smaller. This is because temperatures between 8 to 15 million degrees Kelvin are favourable for this type of fusion reaction. For the higher temperatures of the cores of larger and hotter stars, other fusion reactions are needed. In these cases, the CNO cycle becomes dominant. The proton-proton chain reaction involves three stages. In the first stage, two protons collide to form deuterium, a nucleus consisting of a proton and a neutron, also called heavy hydrogen. There may be many proton-proton collisions, but not many of them produce stable deuterium, since it's more favourable for it to decay back into two protons. In stars about the size of the Sun, deuterium-producing events are relatively rare, so that the complete conversion of the star's core hydrogen would take more than 10 billion years. If deuterium is produced, an antimatter electron, also called a positron, as well as a neutrino are produced in the reaction, as one of the protons had to decay into a neutron. Immediately after this, an antimatter electron would encounter an electron and annihilate each other, forming two high-energy gamma photons. In stage 2, the deuterium fuses with another hydrogen nucleus to form helium-3, a light form of the normal helium. During this stage, a gamma photon is also produced. In the final stage, two helium-3 nuclei fuse to form a single nucleus of helium-4, liberating two protons. Looking only at the reactants and products of this chain reaction, we see 6 nuclei of hydrogen are involved in the chain, which produces a single nucleus of helium with the liberation of 2 further hydrogen nuclei. The net equation is 4 hydrogen nuclei fuse to form one nucleus of helium-4. This produces an overall energy output of about 27 megaelectron volts, the greatest single output of energy for any fusion reaction. The carbon-nitrogen-oxygen cycle is the dominant hydrogen into helium fusion reaction in large main sequence stars. The cycle becomes more and more dominant as core temperatures exceed 17 million Kelvin. This means that it is dominant in stars larger than 1.5 times the mass of our Sun, specifically in O, B, A and F class stars. In G class stars such as the Sun, there is a mix of CNO and proton-proton reactions depending on the temperature. But in K and M class stars, the proton-proton chain reaction is dominant. Unlike the proton-proton reaction, the CNO cycle is a catalytic cycle. The cycle involves the use of carbon-12 as a catalyst, which sequentially captures 4 protons to fuse into helium. In the process, carbon-12 is not consumed and is able to become involved in another cycle. Hence, carbon-12 is the catalyst for the reaction. Initially, a carbon-12 nucleus fuses with a proton and becomes nitrogen-13, an unstable form of nitrogen. In the process, a gamma photon is released. This new form of nitrogen is unstable, and with the formation of a positron and neutrino, spontaneously decays into carbon-13. Carbon-13 fuses with another proton to become nitrogen-14, again liberating another gamma photon. Nitrogen-14 fuses with a proton and becomes the unstable oxygen-15, which decays into a nitrogen-15 when it liberates a positron and a neutrino. Finally, nitrogen-15 fuses with a proton to become two products, carbon-12 and a helium nucleus. The carbon-12 that catalysed the process remains unaltered at the end of the cycle and is now ready to become involved in the process once again. Considering the reactants and products of the CNO cycle, we begin with carbon-12, which sequentially accepts 4 hydrogen to form one nucleus of helium-4, and in the process returns the catalyst carbon-12 to repeat the cycle. Overall, 4 hydrogen fuse to form one nucleus of helium. The cycle's net reaction is the same as the proton-proton chain reaction, and with an overall output of 27 megaelectron volts, it also has the same energy output. Both fusion reactions, the proton-proton and the CNO cycles, produce 2 positrons and 2 neutrinos. The positrons instantly annihilate with electrons releasing 2 high-energy gamma photons. The proton-proton reaction produces a further 2 gamma photons, while the CNO cycle produces 3. These gamma photons will interact with electrons and protons, heating the interior of the star as it makes its way towards the surface. They will constantly be absorbed and re-emitted by electrons and atomic nuclei along the way. The capture and subsequent re-emission into more than one photon causes the photon to be transformed into ones of lower energy. This zigzag journey where photons are constantly being captured and re-emitted may take thousands or even millions of years. Finally, what began as a high-energy gamma photon in the core is radiated into space as one of the lower forms of electromagnetic radiation, from radio waves all the way to visible light and X-rays. What makes the CNO cycle dominant in larger stars is not an increased energy output per reaction, because it's the same as the proton-proton reaction in smaller stars, which is 27 megaelectron volts, but rather it's the rate at which hydrogen is fused in the cycle. Large stars have larger gravitational forces, and as such need greater outward radiant pressure to stop them collapsing under their own weight. The CNO cycle is temperature dependent and converts hydrogen into helium at a greater rate when the temperature is hotter. The larger the star, the higher its core temperature, and this results in a faster rate of fusion to counteract the gravitational forces.
I would I were on yonder hill, it's there I'd sit and cry my fill, and every tear would turn a mill.